So in a laminar flow, for a given flow rate Q, power required to overcome friction. So it is a laminar flow and so given flow rate Q. So the power required, the equation for the power required to overcome friction is proportional to. So we have to evaluate the equation. So this problem is solving by using Hagen-Poiseuille equation. Hagen-Poiseuille equation is used for laminar flow in circular pipes. So this is the equation according to Hagen-Poiseuille. So here delta P is pressure drop in an suppose it's a pipe flow, okay, circular flow of pipe. So fluid is flowing inside the pipe. So according to Hagen-Poiseuille equation, you can find the pressure drop. So delta P is the pressure drop and mu is the dynamic viscosity of the fluid. L is the length of the pipe in which the fluid is flowing and R is the pipe radius. And obviously Q is the volumetric flow rate. So if we know all this value, we can formulate the Hagen-Poiseuille equation, that is delta P, that is equal to 8 mu L by pi R raised to 4. But we have to determine the power required to overcome friction. So that is formulated by using this equation. Not to find the power required to overcome friction, what you have to do is just multiply the pressure drop in the pipe with the flow rate. Okay, so if you multiply the pressure drop in the pipe with the flow rate, we would get the power required to overcome friction. You will get a particular value. Then you have to apply the power more than that. So power required to overcome friction is that much. Okay, so substituting that you get from the option it is Q term, right? So we have 2Q, so usually it will be Q square. So power required to overcome friction will be directly proportional to Q square. So the answer is Q square. Which of the following is a formula for the frictional factor of a circular pipes in laminar flow? So the formula of the frictional factor in a circular pipe having laminar flow, which among these is the option? So for a laminar flow, the frictional factor is 64 by Re. R is Reynolds number, and this equation is derived from Hagen-Poiseuille's equation or Hagen-Poiseuille flow, which is we have discussed on the previous question. So the frictional factor for circular pipes having laminar flow, it should have value that is 64 by Re. R is simply the Reynolds number, and this equation for Reynolds number is rho v d by mu. This rho is the fluid density. I mean the fluid which is used for motion, and then v is the flow velocity, the velocity which is fluid is moving. These the the circular pipes diameter, mu is the dynamic viscosity of the fluid. So for laminar flow, for circular pipes, the friction factor should be 64 by R. For a pipe of uniform cross section, slope of HGL will be. So you have four options. It is compared to EGL, energy gradient line. So with respect to the slope of the high gradient line, what will be EGL? Okay. So this is the definition of high gradient line and energy gradient line. High gradient line, it's the sum of pressure head and atom head of a fluid flowing through a pipe with respect to a particular line. So it's simply the sum of pressure head and atom head. On the case of energy gradient line, there's an additional term that is velocity head. Other two terms are just like a high gradient line. So this is the sum of the pressure head, velocity head, and atom head of a fluid flowing through a pipe. So we can draw a line or a diagram based on the high gradient line and the energy gradient line. So it would look something like this. You can see the difference between high gradient line and energy gradient line is a velocity head, right? All the remaining terms are same for. You can consider both. I mean, elevation head is say present for both the high gradient line and energy gradient line. Similarly, pressure head is also present for both high gradient line and energy gradient. The only difference between these two is the velocity head present for energy gradient line. But as mentioned in the question, we have a uniform cross-sectional pipe. So obviously, when we have a uniform cross-sectional pipe, the velocity would be same. For a uniform cross-section pipe, the velocity would be same by continuity equation. Okay, the area is same, so the velocity ratio should be same. So velocity would be constant. That means this v1 square by 2g and v2 square by 2g will be constant. So will be the slope of the high gradient line and energy gradient line would be equal. Okay, this could vary if the velocity at the inlet and velocity after if it varies, obviously irrespective of the slope of the high gradient line, the energy gradient line slope it could increase or decrease. It could vary with respect to HGL. But since the velocity head is constant due to uniform cross section, we could say this energy gradient line and high gradient line has same slope. So the answer is it is equal to the slope of EGL line. For the same function, psi is equal to minus 8xy, the potential function is. So we have many options. For the potential function, we have given stream function. So, so not to solve this problem, we have to on the relation of u and v. We have stream function psi is equal to minus 8xy, and the relation that is u is equal to minus psi phi by uh, dou phi by dou y, and v is equal to dou phi by dou x. This has to be known, and from that I can write dou phi by dou y and dou phi by dou x. So u will be 8x and v is equal to minus 8y. And the relation of this velocity component u and v with the potential function phi is dou phi by dou x equal to minus u, and dou phi by dou y is equal to minus v. So I'm taking question number 1. Since it's a function of x, I'm integrating with respect to x. So there will be a constant due to integration. And since y is a constant here, so I can write c as a function of y. So differentiating this term with respect to y, so it will be dou phi by dou y, and it will be dou c by dou y, because here c, the constant of integration, is considered as a function of y. So I got one equation, and I also know from y with respect to y I'm integrating from the main equation. So 8y square by 2 plus u of x. So again I can write differentiating with respect to y, it will be dou phi by dou y and will be 8y. So I got two equation of same LHS dou phi by dou y. So equating, we got dou c by dou y is equal to 8y. So if I integrate it, that constant of integration would be 4y square. So substituting that the actual equation, with this equation, you get minus 4x square plus 4y square, and this can be written as minus of 4 into x square minus y square. But when our answer is minus 4 into x square minus y square, you can neglect the sign, sign convention. So sometimes the option won't be the exact match of our answer. So our answer is from the calculation it is minus 4 into x square minus y square, but the options they're pretty much different. So if neglecting the sign difference, it would be very much close to 4 into x square minus y square. From the option, the answer is 4 into x square minus y square. What is a valid potential function? So we have given 4 options of different potential function. So how do you define potential function, whether it is valid or not? Okay, so how to solve this one? What is a valid potential function? So we have given 4 options of different potential function. So how do you define potential function, whether it is valid or not? Okay, so how to solve this one? So not to uh, check whether a potential function is valid or not. So potential function is represented by phi. So not to check whether it is valid, it has to satisfy Laplace equation 2 dimension. That is dou square phi by dot square plus dou square phi by dou y square is equal to 0. If any potential function supposed to be of any function, if it satisfies this equation, then can be said that as a valid potential function. If you check the first option, as you can see, it's some value will be 8, which is not equal to 0. So it does not satisfy Laplace equation. So for option B, where phi is equal to minus 3xy, so as you can see, it is an perfect valid potential function and satisfies the given equation. So the Among these, a valid potential function is option B. So in a steady flow along a straight line at a location, the velocity head is 5 meter and pressure head is 3 meter and potential head is 2 meter. The height of hydraulic gradient line or the head of hydraulic gradient line is velocity at the pressure head and potential head. So we already know from the previous question what is the hydraulic gradient line. It is simply the sum of pressure head and datum head, or we can call potential head. Okay, velocity head is only included in the total energy line or energy gradient line EGL, but for HGL or hydraulic gradient line, it is simply the sum of pressure head and potential head. So the answer will be 5 meter. So Bernoulli's equation is applicable for we have 4 options. So which among these is the correct condition for Bernoulli equation? So I will show you some of the condition for Bernoulli's equation. So this is a condition for Bernoulli's equation. We all know what is a Bernoulli's equation, the simplified form of energy equation, which is derived from the Euler's equation. So the standard Bernoulli's equation is applicable under these four conditions. So whenever you hear Bernoulli's equation, these four conditions has to be satisfied. Should be steady flow. Steady flow means this does not depend on time. Whatever factor is not changing with respect to time. That is steady flow. Incompressible flow means its density is constant. For a varying density fluid means it's compressible. So incompressible density is constant, and inviscid flow means it does not have any viscosity. Okay, it's completely zero viscous fluid and flow along a streamline, or it is having a rotational flow. So among these answer is steady flow, rotation, incompressible flow for Bernoulli's equation to satisfy. A head of 300 meter of water is available in hydroelectric plant. The discharge through the penstock pipe. The flow rate is 200 liter per second. You have to find the maximum power that can be developed from this water. It is stored at a high head of 300 meter and having a discharge of 200 liter per second. And I can use G is saturation due to gravity. And the answer is given in terms of G. So then how to solve this problem? So this is the basic equation for the power developed for a so suppose it is stored at a particular head and having discharge, and if we know the density of that fluid, here the density is water. Okay, they have mentioned this water, so the power developed is eta rho g qh. It is simply rho g qh, but if you consider efficiency, because none of the the power developed by the hydroelectric power plant won't be 100%. There would be obviously some loss, but in this question the efficiency is not mentioned, so the actual equation is simply P is equal to rho g qh. And assuming it to be 100% efficiency, we will get the answer as 60 kilowatt. But we don't have that in option, and that is not possible to develop maximum power. I mean, this is a case of 100% efficiency, then it's not possible. So if you take by a simple logic, if you apply simple logic and say it's make loss 50% efficiency. So by that assumption, I mean the option, the answer would be 30 kilowatt. In a laminar fully developed flow in a pipe, the ratio of average velocity to maximum velocity. Okay, that's a fact that learned by analytic calculation. The ratio between the average velocity and the maximum velocity for a fully developed laminar flow, it is 1 by 2 or 0.5. That means average velocity is 2 times the maximum velocity. Right, average velocity to maximum, sorry, the average velocity will be half of the maximum velocity. Okay, that ratio is 0.5.